The outbreak of the novel severe acute respiratory syndrome coronavirus 2 infection has shadowed a significant impact on every aspect of human society. Many physicians have taken systematic measures to hold off the spread of coronavirus disease 2019, including facial coverings, social distancing, and massive vaccination. Thus, the cases prediction could guide experts to design the future measurements based on the previous cases and other factors, such as vaccination and temperature. There are abundant number of COVID-19 prediction models on the shelf, only use the previous cases, but there are very few models that consider multiple spreading factors. So we propose the multivariable LSTM, SEER-HCD, and mode multi-gate mixture of expert MMOE to perform multi-spread factor prediction tasks. For baseline models, we only use the past cases and simple RNN, GRU, and the LSTM to do the prediction. For multivariable LSTM, we need a way of arranging these variables since the simple LSTM model could only predict based on the one feature. Converting the time series prediction problem into a supervised learning problem by the pandas shift function could help us generate the transform datasets, including the combination of spread factors. Then this dataset will fit into the model to do the prediction. We conducted extensive experiments to explore the advantage of using combined spread factors dataset and multivariable LSTM model in improving prediction accuracy. We could see our multivariable LSTM have a better test MSE than the basic LSTM model. And we also conducted experiments on different combination of spread factors to determine the most relevant factor for cases prediction tasks. At this stage, we find that the full data set of the case, vaccine, and temperature has the best performance.
Okay, in order to validate the trend predicted by LSTM, we introduce another pure mathematical model that is the SEIR. It uses several differential equations to describe the transition rates between different phases of the infection. These phases are suspectable, exposed, infected, and recovered. Here, the uppercase letters represent the starting total population for each phase. And in order to better specify the phases after the infection, we add another 3 new phases into the process, named hospitalized, critical, and death. The 3 new phases are inserted into infected and recovered. So now we have a 7 phases mathematical model. We name it SEIR-HCD. The transition rates among different phases can be described by those equations above. Left side is the transition rate for each phase, and the right side is the computation process. And we have 8 parameters in order to control the trend and then mimic the spread of COVID-19. Next slide, please. On this slide, we show the definitions and functions of these 8 parameters. Among them, RT is the key parameter. It is the reproduction number to control the spread speed of the virus. If it is greater than 1, it means there will be more and more cases, but it is smaller than 1, there will be fewer and fewer cases. And the left 7 ones are some empirical parameters and are summarized from previous data sets. Next slide, please. So here is the prediction result for our new model. The upper one shows the results without intervention. We can see that if there's no intervention, over 8 million New Yorkers will be infected only about 30 days, since there are 330 infected people. But with intervention, we can see that from the lower picture, only about 9% of them will be infected. It shows the efficiency of all the public health policies like requirements of masks and also vaccination. So let's go to Zirui's part.
All right. So when we are applying all different DNA models, we also wonder if our data sets can be polished as well. So we introduced the k-fold cross-validation. It is a method that allows us to mitigate bias and overfitting problems for smaller data sets like ours. So it sounds perfectly to our case. However, it does have a con of losing timing and sequential information, so it might be not really good at prediction tasks. So it basically separates the data sets into k folds, which would train the data sets like k runs, and also for each time it will be one fold that's being used as the testing data set, and also the others will be used as the training data set. So with k iterations, all folds will be used for both training and testing tasks. In order to know how k-fold CV would affect our models, we also have conducted a cross comparison between the vanilla dataset normalization methods as well as this k-fold validation. The results are shown in the next slide. So here, the same baseline model is being used for both validations and normalization methods. The upper one is the vanilla method, and the lower one is the k-fold cross-validation. You can see from the results that the average MAE of the two methods are very close, which are around 1.05 something, meaning that they both don't have much influence against the model's accuracy itself. However, it can be observed that the fluctuation of the upper one is way larger than the one on the bottom, which means that the k-fold cross-validation could mitigate the overfitting problem by just suppressing this way of this errors. For the next slides, please. In this one, we also explored a very popular multitask learning model. It's called the multi-gate mixture of gates model, or MMOE. It's been developed by Google. It compared to a traditional or typical MTL model, the MMOE model has a very different mechanism called expert and a gate that allows a faster and complicated feature extraction and feature sharing. So we initially think that it might be perfect for our task because of its multi-feature extraction, and also it might help us to boost our prediction accuracy. However, it turned out to be that it's only better in multitask learning performances in terms of accuracy, speed of complex tasks, and over large data sets. The prediction is not really good because it lacks of timing mechanisms. Here, the next slide. The next slide shows the comparison of a dual task MMOE model and also two different single task baseline models. The bottom one is the MMOE model, and also it can be observed from the three graphs that the average MAE of all three models are very close, but the MMOE MAE converge much slower than the two baselines. I think it's because the complexity of the MMOE model and also the baseline models are relatively simpler. And here's basically all. Let's go to the next slide for our conclusion.
Okay, overall, a great practice to work through a typical DN training and verifying workflow with multiple models has been done by us. We manually gather and form a novel data set with many factors, try different normalization methods, and also we implemented multi-variable and single variable SSTMs for better prediction performances. Also, to verify the predictions, we never reached a mathematical model to conduct qualitative experiments. And then we minimize prediction errors by adjusting those parameters. Finally, we explored the MMOE model for faster and more accurate feature extraction and MTL capabilities. We proved that the public health policy effectively mitigated the spread of COVID-19 and lowered the rate of fatality. And we believe that this comprehensive learning experiences has added great benefits to our future career and academic advancements. So that's all. Thank you for listening, and also thank for my great teammates. Have a good vacation and Merry Christmas. Bye.